This is problem 40 from the magnetic force. As you can see, this problem is already done for you in the textbook. But I'm going to do it symbolically. It's supposed to be a square loop of wire. I'm going to make it a rectangle. And I'm doing this to teach you some important things, and you should pay close attention because these are guaranteed to make solving problems in this section much easier for you. So, first I'm going to say that this is not a square and this distance is A and this distance is B, so that our result is useful in more general situations. But when we get to the end, if you want to see what it would be for a square, you can just say that A is equal to B. And what they're asking us to do is find the force acting on each side of the loop, and then find the net force on the loop and the net torque on the loop. Okay, we haven't talked about torque yet, but we'll get there at the end of the problem. So the first thing to do is find the force acting on each side of the loop. So again, I'm going to say this is 1, this is 2, this is side 3, this is side 4. And I have my equation, F is equal to IL crossed with B. Let's actually go back and read the problem. It says, it lies in a region of uniform 150 milliteslas. Those are the units for magnetic field. So a uniform magnetic field. I don't think we've ever seen a magnetic field like this before, because in the magnetic field section, the magnetic field was created by a current carrying wire, and the magnetic field was always going in a circle around the wire. So this is a different kind of magnetic field. We're not going to worry about how it is created, but actually in lab you're going to see a uniform magnetic field. It's going to be in a very small region, but it is between two sides of a magnet. So if you have a magnet, you can create a uniform magnetic field. So the way that we would write this magnetic field is the magnitude of the magnetic field, because I'm keeping it symbolic, is just going to be B, similarly to in the last problem when the magnitude of the vector L was L, and in the previous section when the magnitude of the vector ds was just ds, and it's going in the I hat direction. And the length, let's actually write all this out now. So for side 1, the length is A, and the current's going in the I hat direction, and remember that the direction of the vector L is the direction that the current is going in. So this is A I hat. For side 2, the current's going down. That's the minus J hat direction, and since it's not a square anymore, the distance from here to here is B, so that's minus B J hat. For side 3, the distance is A, the current is going in the minus I hat direction, and for side 4, the current is going in the positive J hat direction, and that side has a length B. Okay, so now we're just plugging into this equation here. It's very straightforward. So for side 1, we have the force is equal to the current I, the vector L, which is A I hat, crossed with the vector B. The vector B, since it's a uniform field, is always B I hat. This is I hat crossed with I hat. That gives me 0. Well, we should have known that. I mean, just looking at the picture, if you use your right hand, if the current's going this way, and the field is going this way, well, you can't turn your fingers in that direction because they're already going in that direction. So if it's the same direction as what you started with, or the opposite direction of what you have for your first vector, it's 0. So I hat crossed with I hat gives us 0. And for side 2, current is I have minus B J hat crossed with capital B I hat. So let's pull out the negative sign that we have here first. So let's call that minus I little b capital B, and then just do j hat crossed with I hat. J hat crossed with I hat, if you have to look this up on the green sheet of useful information, you can do that. J hat crossed with I hat, that's not alphabetical order, that gives me a negative k hat. So this becomes positive, and that's k hat. And let's just double check using our right hand. If the current's going downward, and then you curl your fingers in the direction of the magnetic field, your thumb is pointing out of the page, which is the positive k hat direction. Wonderful. Now, for side 3, let's see. The direction is minus I hat. I'm crossing that with I hat. Negative I hat crossed with I hat is 0. So the current's going this way. That's the opposite direction of the field. So we get 0. For side 4, perhaps you can already see what's going to happen here. We have current I. Instead of minus bj hat, we have bj hat crossed with the magnetic field vector. J hat crossed with I hat, that's not alphabetical order, that's minus k hat. So I have minus I, b, k hat. That's the opposite of what we had here. And if you just check with your fingers, current's going up, magnetic field's going this way, thumb points into the page. Okay, now F net is equal to, add up everything we have here, which is I, B, K hat minus I, B, K hat. That is 0. So the net force is equal to 0. I feel like, oh, here, net force is 0. So they did say that. You could check to make sure that if you take the numbers that they gave you and plug them in, you get the same thing here. But let's just check. F top and F bottom equals 0 since the current is parallel to the field, thus the cross product is 0. Okay, and then for the right side, it's going in the k hat direction. For the left side, which is side 4, it's going in the negative k hat direction. So that all looks good. And then they want me to find the net torque on the loop. So the way that we calculate the torque, which we didn't necessarily see in Physics 161 because we didn't call it a cross product in Physics 161. What you might have seen instead in Physics 161 was that the torque was RF times sine theta, where theta was the angle between the vector r and the vector f. I don't know that we really cared in Physics 161 that the torque was a vector. We said if it was negative, then it would be the torque would cause rotation this way. If it was positive, the torque would cause rotation this way. So we didn't really talk about the torque being a vector. We just talked about the sign back in Physics 161, but now we can see that the torque is a cross product. If this is the magnitude of the torque, remember that the magnitude of the cross product is the magnitude of the two vectors times the sine of the angle between the two. So that's where that equation for torque came from. Okay, now it says here to find the net torque, calculate the torque due to each of the side forces using the center of the loop as the origin, and then sum up. Okay, so if we start from the center of the loop, and then I don't have to worry about the top and the bottom because the forces there are 0, so I just have to worry about the two sides. You go from the center of the loop straight to the side, so that's your vector r, and that's not a unit vector, that's that vector. That distance would be half of a. So this is side 2. So for side 2, r is equal to a divided by 2 in the I hat direction. This is the force on side 2. So the torque for side 2 is equal to r, which is a over 2 I hat, crossed with f, which is I, b, capital B, k hat. Now we get to use the right hand rule again. We have I hat, and here, whoops. Oh yeah, the force is coming out of the page. That's in the k hat direction. So r crossed with k hat, that gives you torque going downward. Or we can say I hat crossed with k hat, that's not alphabetical order, that gives me minus j hat. So this is IAB over 2 j hat. Then we look at side 4. For side 4, the vector is going this way, so that's our vector r. The direction changes, but the length is the same, so r is equal to minus a over 2 I hat. The torque, using the force that you have for side 4, this was minus I b b k hat. This is going to give us the same thing that we had for side 2, because I have two negative signs there, which will cancel out and give me positive a I a b over 2 j hat. Let's just check with our right hand. You do the first vector in the cross product, so that's r. R is going this way. Force is going in the minus k hat direction or into the page. Thumb is going down, so that's the j hat direction. Then it says sum up the torque that you have for each side. So to find the net torque, remember that for side 1 and 3 the forces were 0, so the torque would be 0 if the force is 0. So the net torque is equal to what we have for side 2 plus what we have for side 4. IAB over 2 plus IAB over 2 is IAB, and it's going in the j hat direction. What that means is, was it going in the j hat direction or was it going in the negative j hat direction? I feel like I might have missed a sign here. So if I do I hat crossed with k hat, I hat crossed with k hat, yeah, I did say it's going down, and I thought I said it was -2, but I didn't write the negative sign in. And this one is negative because I hat crossed with k hat is minus j hat, and we have negative there. So that's minus j hat, and this is minus I a b j hat. Okay, so if you put your thumb in the direction of the torque, which is minus j hat, then your fingers show the direction of the rotation, which would be caused by the torque. So that would cause rotation this way. So this side would go down, this side would go up. Let's do this. So if the torque is this way, it causes rotation like this. But that is what you would get if you exert a force downward on this side and upward on this side. That is the kind of rotation you would have. Okay, so the two things that I wanted you to learn from this section, actually I think there were 3 things. So the net force on a closed loop is 0, and this is always true. So the net force on a closed loop is 0, and we're going to see why in just a minute. Okay, so that's one important thing. The other important thing is that there's an easier way to calculate the torque. And if you look at what we have here, we started with a rectangle. A times B is the area. So I'm going to say an area vector has a magnitude which is equal to the area. And in this case, the area would be A times B for a rectangle. Okay, so that's A times B. And the direction of the area vector, as we saw when we did the electric field section, before we got to Gauss's law, when we were looking at the area vector, we said the area vector was perpendicular to the surface. When we did Gauss's law, because it was a closed surface, we said the area vector would be pointing outward. But this is not a closed surface, so if you just have the square here, the area of this square, not a closed surface because it does not divide all of space into an inside and an outside. So I don't know what the direction of the area vector should be yet. But remember that every time we've seen it in an equation in the past, it's just the magnitude of the current. So somehow I need to account for the direction of the current. And I'm going to do that using my vector A. And we're going to use our right hand again. If you put your fingers in the direction of the current, going around the closed loop, your thumb points in the direction of the area vector, which we're using the direction of the current for, because I is just the magnitude of the current. So if the current's going this way, then the area vector will be pointing in the minus j hat direction. So the area vector is a, b, minus j hat, where the direction is given by the direction of the current, but you have to use your right hand to figure out what the unit vector would be for that. Wait a minute, that's not j hat. Pointing into the page would be k hat. Okay, so I have my area vector here, and, oh, I forgot something else. Look, I was supposed to have a capital B here, so that would be capital B, and that would be capital B. So there are two other things in my result for the torque. I have the current, and I have B. B was a vector pointing in the I hat direction. So now, watch this. If B is BI hat and A is negative AB K hat, I can say the torque is equal to I A crossed with B. And if I plug in what I have here, just to show that I get the same result, that's minus AB in the K hat direction crossed with B was capital B I hat. So that's crossed with B I hat. K hat crossed with I hat gives me J hat, so that's minus I A B capital B J hat, which is the same thing I got here. Since this was for a rectangle, it could be any rectangle, you could even make it a square, then this equation here must be true for a rectangle. You could even check that it makes sure that it works also when the current is going in the opposite direction, like this, in which case the torque would be in the opposite direction, but this would be in the positive k hat direction instead. So for a rectangle, this is always true. We're going to show in another problem that you can do something similar for a circle as well. So we're going to show that we just showed that it's true for the rectangle. We're going to show that it's true for the circle, and we are not going to show, but it is true in general. So this handout that I'm going to show you now is on the M drive in the magnetic field and force folder. It's called the magnetic force, but instead of calculating the torque this way, for a loop of wire, the torque is given by IA crossed with B, and remember that you use the direction of the current to find the direction of the area vector, because you have two choices for the area vector. The vector has to be perpendicular to the surface, but that leaves you with two directions, so you use the direction of the current to figure that out. Okay, so that was the one other thing. So for a rectangle, we have that. There's one last thing I want to show you here, and that is actually also on the handout, so let's look at this. For a curved wire in a uniform magnetic field, instead of using IL crossed with B, you can use IL prime crossed with B, where the vector L prime is the effective length. So you have a curved wire here, and the effective length vector starts from one end of the wire and it goes to the other end of the wire. And you can use this to show why the net force on a closed loop is equal to 0. So because for a closed loop, the current's going in a circle, you would say that the starting place and the ending place are the same. So L prime is equal to 0. So the net force is equal to 0. So you can use this to show you that the net force on a closed loop is 0. And you can also do something like this. So I'm going to draw a wire here. So if you break this wire up, into little segments, and for each segment, because the wire is curved, you can't use this equation for a straight wire, but if you break it up into small segments, if you do small enough segments, they would be straight, or you can just approximate it as a bunch of straight segments. Okay, so each segment that you have, I'm going to zoom in on this one here. So this vector is going this way. The magnetic field is going straight up. I can break this vector down into components, and I have a horizontal component and a vertical component. But if the magnetic field is going upward, for the cross product, remember, okay, so this piece is a straight piece, so for that piece I can do F is equal to IL crossed with B. And so this piece, this component, is going in the same direction as the magnetic field, so this doesn't give you anything. Well, it gives you 0. So the only part that matters is this piece here. So if I draw my effective length vector from here to here, it's only the horizontal components which are going to give you something here. So even after I break it up like this, I can go like this with my vector, and it's really just this which is going to give me my force, because this component is going to be 0. Or if we had a more interesting shape for the wire where we curl around and go back the other way. So let's say, going back to my square here, if I took this side out, if I go up and then I go over and I go back down, well, when I go up and when I go down, I got the same magnitude for the force on those two sides, but the opposite sign. So going up and going down would cancel out. So if I did the effective length in that case, that would be from here to here, which would be the same thing as what I would get if I do this side plus this side plus this side, since side 4 and side 2 cancel out. Okay, so that's the final important point from this. Not only is the net force on a closed loop 0, but for a curved wire, you can say F is equal to I L prime crossed with B. And the reason that I'm talking about this now is because that equation is going to be important in your lab for this week. Or if you have Tuesday lab, that would be the lab next week.